Hello. So before we start, I want to do a short apology because originally this was supposed to be my talk about async demystified. And as a proper developer, I overestimated my powers and didn't make the talk in time. And rather than bugging you with something half done, I decided to, remove my talk, leave it maybe for next year or for other conferences. And I asked Steve, who kind of was kind enough to reuse one of his talks. And I want to kind of do a little bit apology for myself, for mistaking you. And as well, please be kind of kind to Steve because he got the heads up that he's going to do this talk today at 8 a.m. So I'm extremely thankful that he reused one of his talks, and hopefully the timing will be right, and you guys are going to have a great time. Thank you very much.
Thank you.
And sorry.
Okay, I'm going to get going because, as Carol said, this was a talk that I have presented a few months back, and I had an hour and a half. So I'm going to try and jit this as we go and get a little bit more performance out of it. I've stripped some slides, some bits I may jump over, some bits I may not even remember what the slide was about. But hopefully this will be useful to you. How many people out of interest were in Adam's talk this morning? Because some of this covers similar areas. Some, but not all. Okay, so I will be touching on span of T at one point, and I will just sort of make sure everyone's on the same page. The kind of goal for me writing this talk was that I'm a bit of a kind of imposter in the high-performance space. You've got a lot of great high-performance people here. I mean, Ben Adams, Adam Sitnick, Mark. Lots of great names that do this stuff professionally, and I've kind of been playing around with some of these new features for maybe 5 or 6 months now. And I felt, why not put a talk together about how I learned some of these things and what I was trying to use them for. So there may be some bits that I could probably improve in the code I'm going to show you. There's probably some bits I may get slightly wrong. Hopefully I've researched everything as thoroughly as I can to give you something useful. But I hope this is kind of a bridge for you today between hearing about some of these cool things and seeing what's on the roadmap for Frio and in C# as a language features that we're getting, and some of the core effects features that are available for high performance, and how you can actually take those forward into things you're building. Twitter details, I've done these already. Twitter, website, slides to the probably hour-and-a-half version. I guess that link takes you to, so you'll get extra slides that won't mean anything. But feel free to follow those later on if you need to. People missed that. I'll go back. Cool. So just to set some expectations, kind of along the lines of what I was saying, really, I'm a bit of a sort of newbie to the high-performance world. I've learned about some of these features fairly recently. So from my side, I won't know everything, and I may not be able to answer everyone's questions later on. And then from my side, my expectations of you are I will throw out some terms like GC, Gen 0, some terms that I'm going to have to assume most people have some idea of. So garbage collection, a process to reclaim memory in .NET, generations, I'm not even going to bother trying to explain because I don't have time. But there's a few things that I'm just going to have to assume some knowledge of. But hopefully I'll be able to do a good enough job of explaining the new features that this will still all be stuff that you can kind of take in. So what I'm aiming to cover, most of it, a little bit about what is performance from my perspective, a little bit about how we can measure performance practically. We'll then talk a little bit about span of T, read-only span of T, and memory of T. So this will overlap some of the stuff that Adam probably showed you in better detail and more accurately earlier on. I will try and just sort of cover the highlights there and then show some practical samples of that. ArrayPool, I think Adam may have touched on as well. System.io.pipeline is a favorite of Mark's, I think. And maybe we'll touch on. The things in bold are the things I'm pretty much sure I can talk about. The rest I will see how much time we've got, basically. So from my perspective, one of the things in terms of aspects of performance, I kind of think of a few things that I'm measuring, thinking about in my code. So one of the things is execution time, the raw kind of speed of a piece of code. How quick can I get that? How quick do I need to get that? And that could be individual pieces of code, lines of code. It could be whole methods. It could be the whole request cycle in an ASP.NET Core application. You know, how quick does that need to be to suitably serve our audience, whoever we're building this thing for? I'll talk a little bit about throughput as well, because throughput is a measure that's very much tied to execution time, but it's probably a better measure of how an application is performing overall. So how many requests are you serving? If you're a worker process that's processing things off a queue, how many messages can you process per second? That's a kind of higher level measurement, directly usually impacted by execution time, but maybe more applicable for you to kind of take as a metric and a benchmark. And then memory allocations is the other big one, and Ben hinted at this earlier. Allocations are cheap to allocate memory, but to reclaim that memory does mean that the garbage collector at some stage is going to have to do some work. And if we can avoid giving it that work to do in the first place, then that means we have more CPU time for our code to execute, and generally, hopefully, things should work better. So these are kind of the areas that you're starting to think about when you start looking at aspects of performance. But performance is really very much contextual. I had some slides in here that kind of talk to the kind of early optimization thing, but really it's the point I want to get across with this is that not everything needs to be hyper-performant, but certain things that you're building may be, and you should always be thinking about performance up front to decide, well, what is a reasonable goal for the thing you're building? So when a story is being discussed, a feature is being discussed, or a whole new service is being thought about, what is an appropriate performance level for that in terms of throughput, in terms of resources used on the machine, and then you can see later on if you've actually achieved those goals. And depending on what you're doing, you may want something that's super, super fast and super, super low allocation so that you can get a massive amount of work done very cheaply. Or you might be doing a very general website and you're not too worried about micro-optimizing your code because the ASP.NET team have done a lot of work for you and the .NET Core team have done a lot of work for you to optimize the framework, and you just kind of need to use it. So there's a kind of optimization cycle that's involved in doing this kind of work, and the first step in this cycle is measure. Measuring is super important. You don't want to make any assumptions in benchmarking and measuring of your code. You don't want to just assume that something you've seen online as a way to improve a piece of code will work in your particular scenario, and you don't want to assume what problems you have with your application in the first place. Ben sort of talked about this morning. You may have an idea of what is holding up some process in your application, but you need to prove that. And you need to measure it, you need to profile it, and then you need to get some actual statistical data that you can later use to prove whether anything you've done has had the impact you expected it to. So measure first, and we'll talk about measuring in a moment. The next step is then to begin optimizing in some way. So use those measurements to drive you down a particular hot path in your application or slow piece of code or something that you feel you should be improving, and then have a go at optimizing it. Do this in very small steps. Don't just do a whole swath of changes in your code and assume that they've all had a positive impact. It's best to do small changes, remeasure, and validate each time. So optimize, then remeasure, and get that validation that change made effect. If you just change everything at once and measure it, you may have an overall gain, but you maybe haven't got the full gain that you could have done. Some of those things may have actually regressed, and you just won't be able to see that unless you measure these in isolation. And then just keep going for as long as you want to, and as long as you feel is reasonable to achieve the goal. And this is kind of why it's important to, up front with product managers and people on the team, work out what is an acceptable level of performance for what you're doing, under the conditions that you're in, and then you can just kind of keep this cycle going until either you think there's nowhere to go or you have hit the targets you were meant to be reaching, and then it's probably not worth spending too much more time on it. So measuring, there's many ways we can do it. I know Ben had a huge list of tools up. I've got a shorter list of tools up. These are the ones I'm more familiar with. So at a really basic level, you could use like Visual Studio diagnostic tools, and you could do profiling while you're debugging, essentially. So when you debug, you see the performance tools. It will tell you how much memory is currently in use. You'll see when GC garbage collections are occurring. And you can kind of take snapshots of those things as well if you want to dig into it. You are in debug code at that stage, not optimized code, but maybe it's a good place to start. And then if you want to kind of get into the fully released code, Visual Studio has profiling tools. You can use something like Perfew if you can figure out how the hell you do that. If you want an easier time, maybe .trace, JetBrains .trace, I've been using a little bit, and I found that a little less painful, and I've got less lost. And they also do dotMemory, which we'll talk about later. And there's also tools for looking at the IL code. And you don't necessarily have to be getting down to IR level or even assembly level when you're doing this kind of stuff. But sometimes just inspecting the IL code and seeing what's actually been generated may prove or disprove or lead you down to where something's happening. So you may see virtual calls, you may see boxing occurring in there, things that you can maybe look out for, or just sheer lines of code. You know, how well did the compiler do at actually reducing that down to IL code. The best tool I can recommend for more code level measurements, so those are more general kind of application measurements. Oh God, I've just realized I haven't started a timer, so this is going to be really interesting now. Someone yell at me when I have 5 minutes. The most useful tool for code level is benchmark.net, and thank you, Adam, for such a great tool over there, and the team that work on that. I've sort of been using that quite a lot recently. I found it a really useful way to look at my code and understand, you know, what is it allocating in terms of how much memory and what is its execution time. We'll see that in examples in a moment. And then finally, do think about measuring this stuff in production as well. Your job is not done when you've got to a certain level in development. You want to have metrics and monitoring in place around the stuff that you're deploying so you can actually see how it's performing and you can see if you regress those numbers over time as you do releases. So you know, we use a tool called Datadog at Madgex where I work, so we log a lot of metrics out and we can get idea of throughput and processing times around things there, and we can see if those things change, we can see what commit caused the dips, and we can kind of go and yell at that person if need be. So it's good to have that stuff in production as well. So a little bit more on benchmark.net. Library for micro benchmarking of your code. This is going to give you really high precision measurements over things. The library does a lot of the hard work for you about warming stuff up, pre-jitting code, running enough iterations to get a reliable sample of data. And by doing this, as opposed to maybe just sticking a stopwatch around some code and counting it a few times and going, right, I know the number, benchmark.net is a bit more scientific about how you're going to do it. There's lots of ways you can configure and control it. Using diagnosers to get it to spit out different information, information about the memory used. You may want to actually get the compiled code, the IL code from it. And you can compare things across different platforms, architectures, JIT versions if you want to. So if you are writing code as libraries that may be deployed to framework and core, you can see how the performance numbers stack up on both of those. Just because one's good, the other may not be so good. And this is used extensively by CoreFX, CoreCLR, the ASP.NET team in order to measure what they're doing. And you can go into their GitHub repos and you can see actual examples. Typically in a perf folder, you'll find their benchmarks. And you can kind of see the sort of stuff they're measuring, and you can hook this kind of stuff into your CI pipelines and take these measurements when you need to. So there's some URLs there to go and find more, or probably best talk to Adam, who's taking a photo of that slide. So do you not know this? Good. You can pay me later. So this is what a basic benchmark might look like. Really simple one here. So I've got some code that I want to measure. In this case, I want to measure a method called getLastName on this name parser thing. So I'm going to set up this basic console app, basically. I'm going to use the benchmark.runner in the main method there and point it at a class that contains my benchmarks. I've got my benchmark class marked with memory diagnoser because I want some memory information about this when I get the results. I set up a couple of things, we'll see a better way of doing this later on, but I set up a couple of things outside of my benchmark that I don't care about in terms of measurement. I'm interested in what happens once I call that method. And then this is basically a really simple benchmark that I can now get some numbers about. So we're going to run this. You want to run this in release mode. Make sure you've done so. It will tell you off if you don't. And I forgot that this had all of this fancy stuff, so just pretend you didn't see that. And then you get to the results. So there's lots and lots of stuff spat out at you while this is running. You can see all of the various warm-up phases and things running. And then you get a summary. And this is a good way to get an overall view of things. Obviously, you can actually go and get the data, the full output from this and all of the runs if you want to do a proper statistical view across all of the benchmark iterations. But this is kind of the basic statistical information. So you can see, we ran on .NET Core here. We can see the mean execution time of that method, so 163 nanoseconds. At this stage, we've got no idea if that's good or bad for this app, but I think it sounds all right. It's pretty quick. So at least we know, before we do anything with it, what it's actually taking to execute this. Because I included the memory diagnoser, we can see the Gen 0 collections that would occur per 1,000 operations. And then you can kind of do the math and figure out what that would actually mean, how often you'd have to run this method before you might trigger Gen 0 from the amount of memory it's allocating. And more importantly, really, we can see the bytes allocated. So in this case, 160 bytes. So this is useful information for us to take as our starting point before we would even do any kind of optimization on it. And then we can actually start to use these new features. So I will go through this a little bit quicker than probably normally, because most of you have probably heard some of this morning. But span-of-T and read-only span-of-T are new types that allow us to work with a region of contiguous memory somewhere in a consistent way, through a consistent API, and in a fast and efficient way. So it's in the system.memory package if you need to use it in framework. It's built into .NET Core 2.1. And basically, you're going to get this read-write view over that region of memory. And it might be heap memory. It might be an array or a string that you're looking at, which is contiguous memory. But it could just as well be memory that's been allocated on the stack or native unmanaged memory as well. And so this gives us a consistent surface. We don't have to care about the actual memory underneath. We just care that we're working with this span API when we want to work with it. There's pretty much almost no overhead when compared to sort of iterating over an array natively. So it's worth using. It's pretty quick. It's thread safe. And when you're using span over a string, what you're actually using is a read-only span, because strings are immutable. So it wouldn't make much sense if you had a read-write view over that and you could change the characters in that string. Kind of would upset quite a lot of people, I imagine. So you get a read-only span so that you're guaranteed that you're just getting the view of what that memory is, but you're not going to change anything in there and break code. So these are the kind of two main types. And one of the things I disliked originally is Microsoft did a great deal of marketing around these in terms of, look at this cool stuff we're doing, and this is kind of how it works. But a lot of those posts tended to be sort of suffixed with, but you should never need this unless you're building a framework or you're doing really high-performance libraries, which is somewhat true, but there are places where we're using this that aren't that complex, and it isn't that hard to put this in, and we get a quite big performance gain. And so I don't think you should just rule these out. These are features that are relatively easy to get your head around once you've used them a little bit. So that's why I've tried to include them here as examples. So the key operation that you'll do with a span is you'll slice the span. So I've got an array here that starts off as an int array of 9 elements. I still, to this day, don't know why I made it 9 and not 10, and it really bugs me, but I'm not changing the slide because there's animation. So there's 9 items in this array. Then I can get a span over that by just calling as span. And so now I have this read-write view over the same piece of memory that array was occupying on the heap. At that point, if I want to get a different view on that piece of memory, if I want to kind of look at a portion of it, that's when I slice it. So I call slice. I can give it a start position and optionally the length that I want. And that will result in a new view, a new span. Span being a stack allocator type, it's a value type, and it can never be on the heap, which we'll talk more about. So there's no allocation cost in creating another span here. So now I have this span that represents this inner portion of the data. And if I were working my way through this array looking for specific things or needing to do calculations on specific portions, this is a nice way to do it with no allocations. I'm not copying any memory. I'm not creating new arrays here. And this is a fast, efficient way to do this. It's a constant time operation. So here it's a very short array, but if I were to grow this array to 10,000 elements, the cost and time of me slicing it is exactly the same, because it's really just creating a managed pointer to a portion in this array. It's not actually affecting it. If you do like a copy of this array to get a portion of it, then there is the allocation of the new item and then the copy cost. Question? Yes, it's all safe. Yeah. So let's look at a very trivial example of optimizing some code. I'm sure people will pick apart the actual example that's in here because it's not like the world's best, but I wanted to keep it simple, more to look at the optimization cycle and at the end just an example of where span is used. It doesn't really do anything practical. We'll look at a more practical one in a moment. So the basic concept is I've got this, I've got an array, and I want to get, from the middle of it, I want to get a quarter of the elements. So it's a really random scenario that you're probably not going to get as a business case. But I want to do this efficiently. So that the starting code that our team has written is, well, we'll look at the actual code in a moment, but this is the benchmark setup. So in the global setup, what I'm doing is basically initializing an array of a certain size. Because you don't also want to make assumptions about how performance works for fixed numbers, my average case is that I expect maybe 1,000 elements in this array, but maybe there's more, maybe there's less. So it's good to kind of do some bounds benchmarking around it to see how the performance is across all of those different things. So here I'm using the params attribute to say that I actually want to have this benchmark run 3 times with 3 different sizes. And now this setup method can set up the array at the start of the benchmark, and then we can actually run the code. So, I forget I've got this. This is why I rehearse these things. So this is the actual code. So imagine we'd given that requirement to a developer somewhere, and they very reasonably would probably do something quick and dirty, like they'd, okay, we'll skip the first half of this array. We will then take 1/4 of its length, and we've achieved our goal. Don't worry about the consumer for a second. So that would be the original code we wanted to benchmark. Now, because this is lazy evaluated, you wouldn't get a true benchmark result of actual cost of doing this work. So the consume method here and the consume that was passed in up there are benchmark features to make sure that this is an accurate representation of actually the load of doing this. And so now we can run a baseline against this original developer's code, and these are the results that we get. So you can see we get 3 lines because we had 3 different sizes, and they get progressively slower the larger and larger the array is, and it's saying we allocated 96 bytes, so I'm going to trust that number for now. So I've benchmarked it, and I go along and, okay, well, I think maybe I could use array.copy, maybe that's quicker. So I'll try this approach instead. So this is my first iteration of optimizing that piece of code. We would come in, we get the results, and you can see in red the new numbers, and array.copy is quicker, but it's progressively allocating bigger and bigger numbers because it's creating a new array each time and copying into it, which wasn't happening with the skip and take until we actually start iterating over it, I think. So that's one option, and then I come in again and I go, maybe Microsoft didn't do very well with array.copy. I know better than them. I'm going to try and manually create the array and copy it in and see if I've done a better job. So it's a theory at this stage, and we go, okay, the results. First of all, I'm quicker, I'm better than Microsoft. Yay. And this is why we've done some sizes around this. You know, if we just took 10 as our benchmark, that might have been a completely random number. We might have tricked ourselves into thinking we've done the right thing. But actually, as we see over larger and larger arrays, we're actually losing out. So array.copy is probably slightly more sophisticated than we thought. And so we should move on. And then finally, I'm going to use an example with span here. And basically, we're going to slice this. And then we're just going to return the span of int at this stage. So it does rely on the consumer being able to accept that back and do something practical with it. But imagine we can in this scenario. And so now the numbers look considerably better. On my machine, 10 elements, about 1,000 nanoseconds, 1,000, about 1 nanosecond, and it just stays the same because it's constant time. So it doesn't matter how big the array gets. Slicing is the same time, and we've not allocated anything at this stage because we're still working with the original array that we started with, and then we're just slicing our way into it. So that's kind of the idea of kind of the optimization cycle and a little bit of an idea about using span that I suspect I've misdescribed somewhere. Working with strings, very similar idea. The more practical example here is parsing strings. If you need portions of a string and you want to kind of look at elements of that string or get some data and reassemble it, typically you might do something like a substring or a split. You're allocating new strings there every time because it's immutable, so it has to create that new string. When you slice into a read-only string, a read-only span, over a string, which is an array of characters under the hood, we can access elements of that original string without reallocating anything new. So we can put these things together to start building code that reduces our allocations, and the API for it, in my view, of just slicing into these things is pretty straightforward to get your head around once you've done it a few times. I thought I'd hidden these slides, so ignore that. So some of the limitations around span of t. It's a stack-only value type, so it's a ref struct, which was a new thing introduced in C# 7.2, I think. So it can't live on the heap. It's protected from doing so because this span may have a view over memory that's stack allocated, and so it can't outlive the memory that it's referencing. So it can never be boxed onto the heap. It can't be a field in a class or even a standard struct because that struct itself might be boxed. It can't be used as an argument or a local variable in async methods because those under the hood are going to get compiled into classes and we're going to start breaking the rules above. For a similar reason, you can't capture it within a lambda expression, and it can't be used as a generic type argument yet.
Can you place it within an array of span on a large objective?
An array of span? No, I don't think so. No. It's span of span, that was it, okay. So the main limitations are around that kind of design decision and the fact that it needs to work for all kinds of memory. So if you want to work within those limitations and you've got async code, which is very likely, and you know you're only ever dealing with memory that was allocated on the heap in the first place, you can use memory of t, which is slightly less efficient. It's a read-only struct, but it can be boxed if it needs to be. So it can be used inside async await. And once you've got that memory of t, whenever you're in a context that's safe to do so, so outside, if you call a method that isn't asynchronous, you could then actually pass it a span at that stage by calling the memory span property, and that will give you a span representation of what that memory is currently looking at. So you can kind of use the two together across these boundaries. And don't worry, I've got some code that probably makes this a little bit more concrete in a moment. In fact, now. So putting it into practice, so I've got a scenario that is based on a real one that I've worked with. No one can see me behind those. So we've got a microservice. One of the things it does is read an SQS message. In that SQS message is a JSON message. And what we want to do is we need to store a copy of the message into S3, which is an Amazon blob store, basically. And to do that, what we need to do is give it a unique object key inside that store. And so we're going to use properties that are on this object to generate the unique key. And so that's the scenario. If I jump over to some code. So this was a variant of the original code that we had in this service, which is okay. The primary thing it was doing, so we know that the elements that are used to make up this key are either going to be, there's either going to be 4 of them or 8 of them, depending on whether there's a date in the incoming data. So this event context just contains some properties. I've slimmed it down here. In the actual thing, there's like 100 properties on this type. But we look at those, and then what I do is I create an array of strings. I get the part for each of the things, which is basically just doing a check to see if it exists or not. If it doesn't, we'll just use this unknown part. We then also remove the spaces using this method, so we're just doing a string replace there. And then finally, I need to check if it contains valid keys that are allowed in this S3 naming. So I've just got a regex going on here that's doing that. So I do it for each of the elements I can. For the date, we just take parts of the date. We put these all into a string array. It annoys me there's a space there, so hang on. There we go. And then at the end, we do a string.join on those items, and then we lower them. So this is a reasonable piece of code, but we can have some suspicions about the problems. Now, I promised we benchmarked this, and then we went on and optimized. I'll show you the optimized code versions first, just because it's easier than switching, and then I'll show you the results at the end as kind of an exciting reveal. So the new version we rewrote started to make use of span, and one of the things we did was stack alloc using the span. So we've got a space here that after generating a length, so we do some work up front to work out what elements we've got and how long they are, we can get stack allocated character array on the stack. So we're not allocating anything at that stage. And then once we've got that span, we build in this build part method, we kind of do the same checks that the other code was doing in a slightly more complicated way. And this is one of the things, when you go more performant, you probably go more verbose. So there's another trade-off here around maintainability and performance. You have to decide, is the performance gain you're doing worth the fact that the code might be harder to maintain for your team? How often is it changing, that kind of thing. But very basically, we're checking if we've got a value. If we do, we're going to work out if it's any of the allowed characters using the char is letter or digit. If it's not, then we will get the lower invariant of it, and that will be our data. What we're doing, though, is putting it straight into a slice of the span. So we've got this stack allocated set of characters that we can work with, we're representing as a span, and then we're slicing our way into it to place these bits in the right parts of that span. So I won't go through too much more, but that's kind of all of the code I think I wanted to show. Pretty much, and then at the end, once we're done, we just get the string, because we do actually have to surface a string to give that to the S3 API. It's one of the annoyances you'll find with performance is you'll do a load of work to avoid allocating, and at some point you go, oh, this API needs me to provide it an object, and you allocate. We did improve this slightly in a V2 version, and I appreciate I'm racing through this a little. But this basically does the same thing, but we're using one slight optimization that proved to be a very slight improvement, which is this new string.create thing. So string.create is a way that we can essentially mutate a string for a very short period of time at its creation. So basically what it does is we tell it how much or what the length is of this string that we want to do. It will allocate the appropriate memory on the heap for that. But before it's actually finished returning it, we can pass it this span action thing that lets us pass in a bunch of context for us and then actually work with the memory of that string before it's actually been surfaced to us. The nice advantage here is I'm not stack allocating first, then copying it with the toString. I'm actually working once in the actual memory of the string that I'm going to have. So there's one sort of memory allocation, and then we work with it. And the rest of the code is pretty much the same, so I won't dive too deeply into that. So the main thing, after doing all of that, is the benchmarks. So the original code, when we benchmarked it, was about 1,000 nanoseconds, and 1,144 bytes were allocated in the process of doing that. So we obviously thought we could improve that. So the span-based version got us down to 449 nanoseconds, and the string create slightly quicker. I don't think the 7 nanoseconds are going to really make a huge difference to my life, but slightly faster. That string.create, I think, gets more and more efficient for larger strings than what I was working with, so that's why there's a tipping point, I think, where it's worth doing. But overall, 2.5 times quicker, so that's nice. And 6 times less allocations. And this allocation cost now 192 bytes is the final string. So I can't avoid that because I want a string. But there's no overhead to doing this. So I've just been able to use the concept of slicing my way through or slicing my way through some memory and assembling a string within it by placing characters where I want them, essentially. Now, if I scale this up to this service is actually doing 18 million messages a day we're reading. So I haven't actually put this in yet because people won't let me. But when we do, this, in theory, means that we're allocating 17 gig less per day on that service just by cutting this number down. It really does add up quickly. And we get a massive reduction in the potential Gen 0 collections that we're introducing with this code as well. So that one small change can have quite a big impact when we work out the context of where we're running this. And if we find other places in that code where we're doing similar kinds of work, we can start to make quite big benefits quite quickly. So I want to move on and talk about ArrayPool. And while I'm doing this, I'm going to check when I'm meant to finish, unless anyone knows, so that I don't overrun. So excuse me 1 second. So it's the least professional talk I'm ever going to give. 15:55, cool. So ArrayPool, these basically allow us to reuse arrays. So if we know we're going to be using an array over and over again for some kind of computational work, then it makes sense not to just keep allocating a new array, letting the GC collect it, and keep doing this in some kind of cycle. Array pools allow us to basically ask from typically a shared pool of arrays for an array that's going to be used for some piece of work. So we might use this in some kind of tight loop. You ask it for an array by renting for a particular length. You may get an array, you probably will get an array that's bigger than that length, which is kind of important. So you do need to start thinking about tracking what you're actually putting into that array. The reason for that is for the array pool to be efficient, it can't just give arrays of any size. It needs to put them into buckets, and so it has different bucket sizes. It's going to find the most appropriate bucket that has an available array to give you. You work with that array just as you would a normal array, but what you do when you're done with it is you return it to the pool, and then the next time someone needs one, they can get an existing array. By default, they're not cleared when they're returned. That could be a security concern you need to think about. It's an optimization, but it does mean you may get an array back that has something in it already. If you're worried, you can tell it to clear array true when you put it back. And when you're working with arrays from the pool, you may need to not assume that you've got an empty array to begin with. So don't just iterate the whole array and assuming that all of those data points that were in there are ones you've given it. So there are a few caveats to working with it, and Adam's blog post is a good one. So a very basic idea. So we've got a tight loop that's being called very often, apparently. We're working with a byte array and then passing it on. So we're allocating that array time and time again every time that method gets called. We could replace it with a rent from the shared pool. And now we've got a buffer that we can use that's hopefully not going to have allocated. And what we just need to make sure we do is we return it at the end. So we use a try finally to make sure we do that. Then we've got all the benefits there of avoiding that allocation. So I've got some numbers. I pretty much stole this from Adam's talk, I think. So this only really makes sense at a certain size. If you do it with small arrays, then it might actually take longer to get them from the array pool. So you might avoid your allocations, but you may actually reduce your execution time performance because it's not as quick as allocating. But as you go up in sizes, then the numbers start to look more consistent. At about 1,000 there, it's a lot quicker to do the rent and return, and it's a roughly consistent time as well through rent and return. System I/O pipelines. So this is a feature that I quite like. I've got less practical examples for this one, but it's a new way of thinking about I/O. I think it's sort of a David Fowler piece of magic that he's come up with for efficient I/O, and it was particularly looking at how they could improve like kestrel performance. Basically, it's a bit quicker than working with streams directly. So if you wanted to do efficient streaming without too many allocations, there'd be a lot of boilerplate. It's quite hard to write. Whether you'd get the full performance gain is unlikely. So when you're working with pipelines, you basically let it manage the buffers. The problem with streams is you're creating the buffers for it and passing them in, and there's copies happening all over the place, and that gets inefficient. With pipelines, it's doing the buffer management for you, and it's doing that buffer management from the array pool. And so it can be quite efficient about how it uses buffers. And internally, it will even chain buffers if it needs to, because it doesn't know how much data it's going to get given, so it can chain those as it needs to and give you sequences of those back later on. So there's two sides to it. There's a pipe writer to write data into the pipe, and then a pipe reader to consume. And these are both async. They can be running sort of side by side. Something can be writing at the same time something's reading, until at some point that writer is signaled that there's nothing more coming. And then when the writer's finished with that last piece of data, then they both complete. That's probably all I want to say. There's a big sample here that I will go to talk about, not even talk through because there isn't time, but this is basically, David Fowler has got this example of how you use pipelines. There's a blog post and there's a Channel 9 video, so I'm not going to kind of go through it all because of time, because this would be an hour and a half, definitely. So then we will read. The key point about this is one of the things that's allowed ASP.NET Core to get dramatically quicker and more optimal, because they're now putting a pipe over the request, so you can actually get to the body as a pipe, and this allows them to pass this through the entire ASP.NET stack and stop copying things. And so if you want to work with this data directly, you can also choose to read off of this as well. And so this is just sort of one of the many features that are kind of there for those kind of overall framework improvements that we're starting to see. So putting all of these last few bits into practice, I've got a little demo that uses Spanner-T for parsing, and pipelines are scattered in there for my own amusement. So the scenario here is we're parsing a set of files that are CloudFront logs from AWS. So these are just tab-separated files with some number of lines in them, and we want to get from 25 of those columns, we just want data from 3 of them. And we want to read that out and index that data somewhere. So the way we were doing that, or one of the ways we were doing that originally, looked a little like this. I've had to kind of cut these demos from our main code and make my own simplified versions. But this was, I'm not going to name the colleague, but my colleague wrote some code, and it's fairly evident that it's probably allocating in here. So they get in this case, I'm getting a file stream rather than an S3 file. But we get the stream, we decompress it, and then he copies the entire bytes from that decompressed stream, uses it to get the string representation of the data of that file, and then later uses this library called Tiny CSV Parser that also works with tab-separated files, which makes it quite quick and simple for us to just kind of get the columns out that we care about. But it does take this string input. But there's some sort of warning flags in here. Again, we benchmarked, but there's an allocation here probably. There's an allocation of a string. God knows what that library is doing, so we thought we'd better check that out, and we benchmarked it. And so the result of our work on this was an optimized one, but the key thing is more code, less easy to follow, and so again, it's contextual whether this is worth doing for a particular code base. But here I'm getting a pipe reader off of a stream using pipelines.sockets.unofficial, which is one of Mark's things. And this lets me have this pipe reader that's just coming in off a stream. So I can now work with the pipe reader using its kind of typical patterns. So I read some stuff off the pipe, and then I parse to see if there's any complete lines of data in the file. And if there is, then we'll parse the actual line. And what I'm doing here is I'm just slicing my way through that span that represents the text of that line, looking for the index of tabs, because I know it's tab separated. And then I can go through and find, I only need only 3 columns. They're in the first 12 of the 25, so I only look as far as 12 tabs in. And then if I find the tab count that I want, then I actually go and get the string value which I need. So I'm only allocating strings where I really have to here. I'm not putting it through this wacky library that I don't understand. And the results of doing this, so again, not too complex. It's a little bit of work to figure it out, but just slicing my way through in a loop, basically. And then we ended up with these kind of numbers. So for 75 files, 10,000 rows, we got execution time quite dramatically reduced, 7 times quicker. Allocations were worse, according to the benchmark. And this stumped me for a while, and I spent a little while working out what I was doing wrong, and then I messaged Adam, and I said, what's happening? And he explained that, unfortunately, .NET Core doesn't expose, or didn't expose, an API internally for measuring the allocations across threads. And so this code is very async await-based. And so benchmark.net's not able to get accurate numbers from .NET Core. But in the new version, that's been fixed. So coming soon in like Preview 7 onwards, or Preview 6 actually has got it, that's fixed, and you'll be able to get accurate benchmarks. But I had to head back over, and instead I put this through dotMemory. So I basically just looked at the memory traffic of running this code. So the actual memory traffic of running the original version was 7 gig for this set of 75 files. After optimizing, I was down to 208 meg, so I felt pretty good about that. I also looked at it, and when I sort of looked at the actual data, 203 of that are the strings that I had to allocate to index into Elasticsearch. So they're the actual output that I kind of unavoidable, so the overhead's pretty low. I am now looking at Elasticsearch support putting bytes in directly, and so I'm thinking I can probably avoid the string allocations entirely soon. But it's still a lot of an improvement just from applying a few techniques. And again, at scale, this starts to really add up. I'm not sure I've got much time for these. There are new JSON APIs in .NET Core 3.0. A lot of people may ask, why have Microsoft rewritten JSON libraries? We've got JSON.NET, open source, Microsoft hate them. But that's not really the case. JSON.NET was developed at a time before all of these high-performance features were available, and it's very much around parsing and things like that. It would be bloody hard to change that today without breaking a lot of people. And James Newton King, who has been snapped up by Microsoft to avoid him yelling about this, who actually does agree that this is a good idea and that we can write a more focused JSON library that's particularly around web UTF-8 data parsing in an efficient way that takes advantage of things. There's some low-level APIs that you might work with for really efficient code that you're trying to write, but then you can get these sort of higher-level abstractions up to a serializer that may be slightly more generic in terms of the performance profile, but they'll still be a lot better than JSON.NET. I think some of the figures are sort of 2.5 times quicker for a lot of common scenarios, and there's possible future plans there. To briefly show you in 3 minutes what that code might look like in here. So I've got this, that's revealing the new one, bulk response parser. So the basic idea is I'm doing some indexing into Elasticsearch manually through their REST API. I'm bulk indexing some data, and I want to know if any of those indexing of documents failed, which IDs failed. In the scenario where nothing fails, I don't really care. I just want to move on with my life because I'm happy that everything's okay. So the original code would just deserialize the bulk index response and then see if its errors property is false, and if so, I know that I've got no errors and I can return an empty array of the IDs. Otherwise, I have to iterate through and find the errors. And this works fine, but in the new version, what I did was, this time I didn't use pipelines, but I've just worked with the stream and get chunks off of the stream, pass it into this method where I have one of those UTF-8 JSON readers. This is reentrant, so it takes some state. If you're coming at this multiple times, you can kind of keep coming through with chunks of the JSON data that you want to work with, which is just a read-only span of bytes. And then you just read your way through it, looking at the JSON tokens. Now, this is lower level code than you might want to write in most cases, but it means I could only take notice of the JSON properties I cared about, and I could avoid collecting any data about those that I didn't. So I work out basically where I am in the document and start taking data from it. The nice thing about this is here, I check partway through this if I've found an errors property and whether it has errors or not. That's within like the first 20 bytes of the response. So if I find that and it's got no errors, I just jump straight out of this and move on. There's no reason for me to parse any more of that message, whereas JSON.NET had to fully parse the object for me to find that out. So that means that in the happy path, I can get a bit of a gain. Yep. So I took 2 measurements, so one on a failure response, one on a normal success response, which is the happy case that I expect like 99.9% of the time, hopefully. But if there is a failure, then parsing it through the new method was quicker and allocated less. I was still curious why 16K, but still, I'm probably doing something wrong there. But still a lot better than parsing it through JSON.NET and relying on actually serializing the whole object, or deserializing the whole object. On the success response, because of that quick happy path sort of escape that says once I've read a property that says there's no errors in here, I don't bother parsing the rest of it, it's really, really, really quick. And it only allocates 80 bytes in the process of doing this. So this simple change was really powerful. Now, to wrap up and put this all into perspective, we've looked at all of the techniques so far that I've been working with. Just one of our microservices, and we tried to work out what sort of potential gains we've got about investing time. We're trying to convince the business at this stage that maybe it's worth doing some performance work. So we sort of got all of the prototypes together, and we said, well, for this service, our input processor, again, it's another one that's dealing with 18 million plus messages a day. We can see that we can probably reduce at least 50% of the allocations just using some of the techniques we've looked at so far across a few key areas. We believe we can at least double the throughput of that by reducing the execution time of those pieces of code. So we can kind of do the math and go, actually, we don't have to scale this microservice as much as we have been, and that might save us approximately 1 VM of scaling, because it's in containers, but we're having to scale the VMs underneath those containers as well. So if we can reduce that 1 VM cost, that's $1,700 a year. We have to prove is that $1,700 is worth the time it takes to make the code changes, but we're very convinced that with the prototypes already, we could probably do some of this work in a few hours. There's some quick wins in there for sure, and it very well be worth pushing the business this way. And then we've got many microservices, as is the idea of microservices. So if we can apply this across the board and start reusing the same techniques across all of those, what potential have we got to reduce our business costs? Because ultimately, that's what's going to convince your stakeholders that it's worth you investing some time in this, and that's what makes it contextually worth you doing it in the first place. I'm over, I think, so I think we'll let people read the summary. And thank you very much for listening. As I say, the slides are online. I know that was a bit sort of broken. I think I remembered most of it. If there's any questions, I think maybe catch them later in the performance panel, probably. Thank you very much.